This video lecture addresses applications in the field of remote sensing and geographic information systems, with a specific focus on hydrospheric sciences. First, we will explore why the field of remote sensing would be concerned with the hydrospheric sciences. And then we will further discuss how the field of remote sensing can capture useful information for environmental science and management issues. Some 3/4 of the surface of planet Earth is covered in water, with the majority being in the oceans. In the table here, presented by Campbell and Wynne, we see that by both surface area and volume, the percent of water in the oceans far exceeds other stores of water on Earth. And yet fresh water, like that in rivers, lakes, and aquifers, despite contributing less than 1% of the total volume of water on Earth, has a profound impact on human society. As well, changes in surface area of sea ice have profound impact on climate regulation, though only approximately 5% of the surface of Earth is covered in permanent ice cap. In this example, we see two images captured by the Moderate Resolution Imaging Spectroradiometer, MODIS, flying on the Terra satellite. The story by the National Aeronautics and Space Administration, NASA, 2014, presents the research interests of climate scientists Johnny Ryan of Aberystwyth University and Jason Box of the Geological Survey of Denmark and Greenland, and their investigation of the dark ice, which is the permanent ice sheet. As NASA notes, quote, fresh snow has an albedo of about 0.86, meaning it reflects about 86% of the sunlight that hits it. The darker underlying ice can have an albedo as low as 0.3. Since it is much less reflective than fresh winter snow, dark ice absorbs a much higher percentage of incoming sunlight, warms the surface faster, and hastens melting. End quote. As background, the Greenland ice sheet holds some 8% of the fresh water on Earth. With the loss of the entire ice sheet, global sea level would rise some 7.4 meters, 24 feet. As Campbell and Wynne note, quote, the spectral qualities of water bodies are determined by the interaction of several factors, including the radiation incident to the water surface, optical properties of the water, roughness of the surface, angles of observation and illumination, and, in some instances, reflection of light from the bottom. End quote. The volume reflection, or the energy scattered and reflected within the water body, largely determines the spectral signature of a body of water. Note that as impurities like sediment pollution are added to a water body, the spectral signature changes. Consider the graphic shown here from the Science Education through Earth Observation for High Schools SEOS, which shows the reflection of water, blue line, vegetation, green line, and soil, brown line. You can imagine that as additional sediment is added to the water column, the reflectance will change. In this example from the Earth Scan Laboratory, Coastal Studies Institute, Department of Oceanography and Coastal Sciences, School of the Coast and Environment, Louisiana State University, a project by Principal Investigator Non Walker focuses on coastal restoration efforts that are part of the Mississippi River diversions in the Gulf of Mexico. Recall that materials move through suspension and solution in water, so the levee system installed along the Mississippi River over the previous decades have diverted the freshwater inflows. In restoration, these diversions act as breaks in the levee system in order to provide freshwater flow from the river along with its sediment load and associated nutrients, which helps build salt marsh and dilute salinity levels. Remote sensing applications allow real-time and long-term surveillance of measures such as sea surface temperature and suspended sediment. As the SEOS notes, quote, remote sensing is based on the measurement of reflected or emitted radiation from different bodies. Objects having different surface features reflect or absorb the sun's radiation in different ways. The reflectance properties of an object depend on the particular material and its physical and chemical state, for example, moisture, the surface roughness, as well as the geometric circumstances, for example, incidence angle of the sunlight. The most important surface features are color, structure, and surface texture. These differences make it possible to identify different Earth surface features or materials by analyzing their spectral reflectance patterns or spectral signatures. These signatures can be visualized in so-called spectral reflectance curves as a function of wavelength. End quote. Looking at the image here, and in keeping with the theme of applications of remote sensing in the hydrospheric sciences, the SEOS asks, what are the blue circles? Displayed in a false color satellite image, the blue circles are irrigation fields in the desert of Libya near a city, which is apparent in the upper left side of the image. Consider what colors you would expect to see if instead this image were portrayed in true color, thermal infrared, microwave, LiDAR, or other image acquisition possibilities. CFASTI offered these images of center pivot irrigation in the desert, where each circle has a 0.5-mile radius. The images were captured with a handheld camera by a passenger in a Boeing 757-300 and then processed on a computer to pull out the band combinations and to calculate the Normalized Difference Vegetation Index, NDVI. These center pivot irrigation circles were captured near Unionville, Nevada. The RGB presents a combination of red, green, and blue, which is a true color image. The infrablue image displays a false color image since the infrablue filter prevents the passage of red light in the 600 and 700 nanometer wavelength range, but allows near infrared light in the 700 to 1000 nanometer range to pass through, as well as shorter wavelength blue light. The NBG presents a combination of near infrared displayed as red, blue, and green. The NDVI is calculated as an equation where the difference of near infrared and visible light is divided by the sum of near infrared and visible light for each picture. This is another set of interesting images from CFASTI, showing the eastern shore of the northern end of Great Salt Lake in Utah. The photographer suggests that the color along the shoreline apparent in the RGB image is from the red algae Dunalia salina and Halorheiaceae bacteria. Here is another application of remote sensing to the hydrospheric sciences. The following resources were consulted in developing this video lecture on hydrospheric sciences in remote sensing and GIS.